Hi, welcome back to General Chemistry 1. I'm Dr. Fang Xu. In this video, we're going to talk about Lewis structure and formal charge. Lewis structure or Lewis dot structure can be used to describe the electron configuration of an atom or molecule, and we only talk about the valency electrons. So in the Lewis dot structure, each dot represents one valence electron. And for main group atoms, the number of valence electrons equals to the number of the group before A. So say oxygen is in the 6A group, and then the valence electron of oxygen is 6. There are only 4 different equivalent directions for Lewis structure as for valence electrons. And in each direction, it can hold up to 2 electrons as a pair. Just giving an example about how the Lewis dot structure works for an atom. Say lithium is in the 1A group, so it has only 1 valence electrons. We put 1 dot here around the lithium symbol to represent the 1 valence electrons of lithium. But if we move to fluorine, it's in the 7A group, so there are 7 valence electrons. We put it into 4 different directions, and each direction can hold a pair up to 2 electrons as a pair. So it has 3 directions that have electrons in pairs, and 1 direction has a single alone electron. And for neon, it's a noble gas. It has 8. It's in the 8A group, so it has 8 valence electrons. All the electrons are in pairs in 4 different directions around the symbol. Yeah, so the easier way to write this Lewis structures of an atom is to first count how many valence electrons are there from the column's name, and then put 1 dot in each of the 4 directions, and then start to pile them up until you use up all the electrons. Okay, so after we know the Lewis structure of an atom, we can move on to know the Lewis structure of a species. It can be a compound, it can be diatomic molecules, it can be anything. Okay, it can also be an ion. For example, this is the Lewis structure of a molecule. Boron is in the center. Well, there are fluorine atoms, 3 fluorine atoms around the boron. And each stick here, it's a bond. And you can see there are some dots around the boron, around the fluorine. These are the Lewis dots that represent a valence electron that only belongs to the atom next to the dots. In this case, only belongs to the fluorine. And between fluorine and boron, there are sticks. These refers to the chemical bonds. If we have a single line, then it refers to a single bond that is equivalent to 2 valence electrons. If we have a double line here, then it's a double bond that corresponding to 4 valence electrons. And if we have 3 lines between 2 atoms, it's a triple bond that corresponding to 6 valence electrons. All of these chemical bonds that are connected, that connects 2 atoms, refers to the electrons, valence electrons shared between these 2 connected atoms or bonded atoms. Okay, so besides molecule, we can also use Lewis structure to write an anion. Here's an example of the nitric anion. We have nitrogen in the center that binds with 3 oxygen atoms around it. So you can see we have a bracket, and on the right superscript of the bracket, we have negative here. This negative sign refers to the charge carried by an anion. Here we leave out the numerical number of 1, and the default value of the negative sign is -1. Okay, and the main body of the structure of anion is put in the brackets. Okay, as you can see here, nitrogen is in the center. It has a double bond to a top oxygen, and this oxygen, the top oxygen has 4 valence electrons as 4 Lewis dots in 2 pairs in 2 different directions. So all of these 4 directions of Lewis dots are equivalent. So instead of putting these 2 pairs as left and the right, we can put it in the top and the right, top and left. Any 2 of the 4 direction is fine. The direction formed by a bond is occupied, so we don't put Lewis dots in that direction. And finally, we can use Lewis structure to write a cation. However, for cation, because it's loose electrons most of the time, loose valence electrons, all of the valence electrons. So Lewis dot structure of a cation is the same as its formula. Okay, so after we know the Lewis structure, we're going to talk about in our next video on how to write a Lewis structure from a chemical formula. But in this video, we want to touch base on how to calculate the formal charge. That is one of the criteria used to determine whether a Lewis structure is correct or not. So what is a formal charge? Formal charge is a charge an atom would have if the bonding electrons were shared equally. Okay, it's the definition. So by the definition, we can use this formula to calculate the formal charge. This is very important, so please remember this formula. The formal charge of an atom equals to the number of valence electrons of that atom in the periodic table minus the number of unshared valence electrons. This is the valence electrons or dots you find in the Lewis dot structure, and then minus bonds. If it's a single bond, you -1. If it's a double bond, you -2. Triple bond, -3, so on and so forth. Yeah. So this is an equation I found easier to remember and easier to use, or you can use the equation from the textbook. The formal charge of an atom equals to number of valence electrons minus the sum of number of unshared valence electrons plus half of number of shared valence electrons. Half of number of shared valence electrons equals to the bonds. So let's take a look at the example. Calculate the formal charge of each atom in the Lewis structure. Here is a structure of boron fluoride. Boron is in the center. It has a single bond to fluorine, and each fluorine has 6 Lewis dots around it. So you can take out a spreadsheet, pause the video, and try to calculate the formal charge of boron and fluorine by yourself first. Okay, so for boron, it's the 3A group element. So the number of valence electrons of boron is 3 in the periodic table. And then it should minus the number of unshared valence electrons. Here in the Lewis structure, there's no dots next to boron, so that part is 0. And then minus how many bonds. So the boron has 3 single bonds, so it's 3. So for boron, the formal charge is 3 minus 0 minus 3, that equals to 0. And also for the fluorine, all of these fluorine have the same environment. All of them have 6 Lewis dots and 1 single bond. So for fluorine, the number of valence electrons is 7. It's a 7A group element. So 7 minus number of unshared valence electrons, that's how many dots we have, that's 6. So 7 minus 6, then minus how many bonds attached to each of this fluorine atom, that's 1 single bond. So the formal charge for fluorine here, all of them are the same. All of the fluorines are the same. So formal charge of fluorine atom is 7 minus 6 minus 1, that equals to 0. In this Lewis structure, both boron and fluorine have a formal charge of 0. Then how about this one? 3 oxygen next to each other. It's an ozone. On the left, we have oxygen with 4 Lewis dots and a double bond to the central oxygen that has a pair of Lewis dots and an extra bond, single bond with the third oxygen atom that has 6 Lewis dots. You can try to calculate the formal charge of each oxygen here. Okay, so to clarify which atom is which, I label all of these oxygen atoms from left to right as 1, 2, and 3. So for oxygen 1, oxygen, all of the oxygens, the number of valence electrons for an oxygen is 6, as it's in the 6A group. Okay, so oxygen 1, it's 6 minus 4 dots minus a double bond, that is 2. So for oxygen 1, the formal charge is 6 minus 2, 4 minus 2, that equals to 0. For second oxygen, it's 6. The number of valence electrons for oxygen. So 6 minus 2 dots minus 3 bonds. So it's +1. And for third oxygen, it's 6 minus 6 dots minus 1 bond, that is -1. Okay, so you can see here, the oxygen number 2 and 3 does not have a formal charge of 0. One is +1, one is -1. Okay, after do the calculation, we can know a few rules of formal charge. As you probably can tell from these two examples, the formal charge we calculated for a correct Lewis structure are very close to 0. Yeah. So the sum of the formal charges of all atoms in a species should equal to the overall charge of the species, overall charges that species carries. So for example, here, boron fluoride, we calculate all of the formal charge of atoms are 0. So the sum of the formal charges are 0, and that's equals to the 0 charge this molecule carries. It's a charge neutral atom. Or if we have a sulfate, here a Lewis structure is shown. A sulfate carries -2 charge, and if you add all of the formal charge of each atom here, including 1 sulfur and 6 oxygen, the sum of these values, the blue values, the formal charge values, are also -2. So sum of the formal charge equals to the charge that this species carries. And then second, the formal charge of any atom in a stable Lewis structure should be close to 0. So when I say close to 0, 0 is obviously the best, but you can also have +1 or -1. So very rarely you will see +2 or -2, but that's very, very rare case. Okay, so for example here, if we have 3 different Lewis structures of NCO molecules, the formal charge is calculated showing up in the blue number here. So the first one, the nitrogen has -2 formal charge, oxygen has +1 formal charge, nitrogen has -1, carbon oxygen has 0, or nitrogen and carbon has 0, oxygen has -1. Obviously, the first molecule has a larger formal charge, which is not necessary. So we say this is not a stable Lewis structure, while the second and third Lewis structure are stable. Okay. A few others say a formal charge closer to 0 is preferred. It's basically the same thing as the second bullet point. And then the same non-zero formal charges on an adjacent atom are not preferred. So say if we have carbon here as +1, oxygen as +1, they are the same formal charge on the next to each other atoms, is not preferred. When we say it's not preferred, we really, in the general chemistry scope, we say it's wrong. You need to recheck the Lewis structure and see if there is any mistake. And also, finally, a more negative formal charge should reside on a more electronegative atom. So here for carbon and oxygen, oxygen has a -1 formal charge and oxygen is more electronegative than carbon, then that's fine. However, if we imagine we have a carbon has +1, a -1, and then oxygen has 0, then it's not preferred, it's not correct, as more negative formal charge should reside on a more electronegative atom. All right, this is the end of this video, and I'll see you next time.